I'm going to talk about joint work with Andres and also with Ivan, who's not here, from Zaragoza. So the title is Butson Full Propelinear Codes, which means I will be talking a bit about codes, but for the benefit of the audience here, I'm going to try and keep things more on the Butson end of the title rather than the codes, but everything will come into play. So, I point here. Okay, so just to clarify some notation that we'll be using throughout, typically n and k are going to be positive integers. N usually means the length of a vector or the order of a matrix. K is usually used in the context of root of unity. So zeta k is going to be the primitive kth root of unity, defined like so. When I use the angle brackets, that means I'm taking the set of all kth roots of unity, or if you like, the set generated multiplicatively by the primitive one. Mn will tell me it's the set of n by n matrices with entries in whatever the set is, usually the set of kth roots. And mon nk is just a set of n by n monomial matrices, meaning exactly one non-zero entry in each row and column, and that non-zero entry will come from the set of kth roots. So this is all fairly standard. What I also want to highlight, which is probably a little bit less commonly used, at least in this conference so far, that is, when I have one of these matrices, these n by n matrices in the kth roots, then we will take L of m to be the matrix that we get by just taking the exponents of that primitive kth root. So entry-wise, yes. So here's an example where I have third roots to whatever the power is, and in this matrix, we're just taking the powers. So that's convenient both for just writing it down in a easier to see way, but we are actually also going to be using these matrices, treating them as having entries in the integer ring modulo, in this case 3, but modulo k in general. So it is an important distinction to make. So I can probably gloss over a lot of the introduction stuff because I have the benefit of talking on day 3, and you all know what a Butson matrix is, but just for completeness, I typically use the notation m star to mean complex conjugate transpose. Transpose is actually missing here. And then the definition of a Butson matrix you've seen a number of times, but just to reiterate, it's an n by n matrix with entries in the kth roots. Multiply the matrix by its conjugate transpose, I get n times the identity. That's a Butson matrix. And the set of all of those will be denoted by bhnk. Okay, so you've seen lots of these. One example that I want to present, not because I think you need an example of a Butson matrix, but because I actually also want to introduce this notation. If I have a prime number p, then if I look at the vectors of length n, entries in zp, and then take the matrix that I obtain by looking at the dot products of every pair of vectors, or if you like, x times y transpose, then I get a matrix with the entries in zp. And then if you treat that as the exponent matrix of a matrix in the pth roots of unity, then that matrix will be a Butson matrix. So it'll be p to the n by p to the n in the pth roots. And this is well known. It's the Fourier matrix of order p, Kronecker product with itself n times, also known as the Sylvester matrix when p is 2. And this D will always be this matrix for the rest of the talk. So occasionally you will see D or L of D will come up. I mean this one. Okay. Now, Santiago took care of this for me, so I can gloss over this because it's almost identical to what he had on his slide. So this is where we talk about the notion of equivalence. And just like he did, I do it in terms of a group action. So I take pairs of monomial matrices, n by n in the kth roots, and those pairs act on some n by n matrix in the kth roots, like so. P on the left, Q star on the right. The star on the right is so that it really is a group action. And then two matrices are equivalent if I obtain one from the other using this action. So this means I can describe the equivalence class as just the orbit under this group action. And then as Santiago described, we can talk about the automorphism groups, again using this language. The automorphism group of a Butson matrix is the stabilizer of the matrix under this action. And then the permutation automorphism group is the stabilizer under the action where you restrict to permutation matrices as opposed to monomial. So the other thing that Santiago also dutifully took care of for me is the notion of a co-cyclic matrix. So did Andres. So I will very much gloss over the details here. But just to remind you, I've got finite groups G and U. U is abelian, doesn't matter what G is. Orders n and k respectively. And then I have to satisfy this equation for every triple of elements x, y, and z in G for my co-cycle psi, or for the map psi to be a co-cycle. So you've seen it described as a 2 co-cycle already. I'm just dropping the 2 because I only talk about this type. So as you've seen, this forms a group. I think Santiago said under addition. I say under pointwise multiplication. I guess it just depends on how you write these things down, but same idea. And we can describe every co-cycle as a matrix. Pretty simple. You just index the rows and columns of your matrix with the entries in the group. So in the row labeled X, column labeled Y, I put in the entry psi of the pair X, Y, and that is my co-cyclic matrix. So in particular, if I'm talking about Butson matrices, then my matrix is co-cyclic if it's in the same equivalence class as something that is co-cyclic according to this definition here. Now, finally, I think I can move on to at least one of the other words in my title. So as promised, I will talk a little bit about codes. And to start off, I'm going to tell you what I mean by a Butson code, and then we'll move on to the rest of the description. So we start off with a matrix H that is a Butson matrix. And then what we do is we just take this matrix of the exponents and then treat that as a matrix over the ring of integers modulo k. And then the vectors that are rows of that matrix we can take to be code words. But we extend this a little bit and we get CH, which is the set of code words that we get by taking those vectors, but also every vector that we can get by adding an all ones vector to it as many times as the alphabet allows us. So if I have a BHNK, I get n code words from the matrix itself, but I also get another n code words by adding the all ones vector once and then again and again. And I have n times k vectors altogether, all of length k. And that's CH. And again, unfortunately, I'm going to have to ask you to remember that that is how CH is defined because it will recur. It's not linear. It is not linear. No, it is a very basic definition of a code in the sense that it is just a set of code words. It is not linear. So when you're talking about codes, you're interested in isometries, which typically preserve distance or Hamming distance. So isometries of vectors of this type take this form. We describe them as a pair, sigma and pi. Sigma is an n-tuple of permutations of the symbols in your alphabet. So in this case, it's just something that permutes 0 to k minus 1 in some way. And then pi is some permutation of the n coordinates of your vector. So it's some element of the symmetric group on n elements. So these isometries form a group, and the action that they have on vectors is defined like so. This is just how the action works on the vector. You can apply the permutation of the coordinates first, and then the permutations of the symbols. And then you can see how it's composed here. The details are not so important. So now I get to tell you about what I mean by a propylinear code. So this is probably the first word that most of you don't know unless you have already been closely following this kind of work. So here we take a code of length n over the integers modulo k. Again, we're not talking about linear or anything. We just have a set of code words. And we say it as a propylinear structure if for every one of these code words, I can associate the isometry. So I've got a pi x that depends on x. I've got a sigma x that depends on x. And I have to satisfy a couple of properties. One is that applying the isometry for any of the isometries associated to any code word x, I should preserve the set. and I should also take the 0 vector and send it to that code word X. The second property that we need to satisfy is sort of more of a group theoretic type property. And that's where if I can obtain some vector Z by applying an isometry associated to X to some vector Y, then I need to have this relationship between those isometries based on the composition that you saw in the previous slide. So if my code has this particular structure, then this is what we call a propylinear structure, then we can associate a binary operation with this set of code words, where this binary operation star, I compose X and Y by letting the isometry associated to X act on the vector Y. And this is for any pair of vectors in my code. So what this means is that this set of code words now forms a group, because these conditions essentially imply that I will always have closure and I will have inverses and so on. It maybe takes a little bit of details to work out, but these code words now form a group with this operation. It's not abelian in general, and this is what we call a propylinear code. So this generalizes linear codes in the sense that if you were to take the sigma isometry associated with X to be equivalent to just adding the vector X to whatever it's acting on, and if you treat the pi, this permutation of the coordinates, as being trivial, just always the identity permutation, then what you're left with is a set of code words that have an additive structure. And if you have a linear code, it's exactly this, and it just means that your group is elementary abelian of order, I guess if it's a code over the field of order Q, it's Q to the n, whatever. So you've got an elementary abelian group where it would just be vector addition would be the same as this star operation. So this generalizes linear codes in a sense. So one of the reasons that we're kind of interested in these objects is because it does have one of the same advantages from a coding theory perspective that linear codes offers, which is that with a linear code, you can just store a generator matrix, and then that generator matrix has all of the information you need for the code. And here, because this has a group structure, it means all we need to store are the generators of the group and the relations. So we don't have to store all of the code words, we just store the group generators. So it retains that advantage from linear codes while offering a different kind of structure that we might be able to exploit for various reasons. So the next part of the definition is what we mean by a full propylinear code. And this is the last word that I hadn't described in the actual title. And a full propylinear code is just a particular type where I do have a specification on how sigma works. And it is exactly like I described in the linear case. If my sigma associated to A acts on X by just adding the vector A to X, standard vector addition style. And I have a condition that the permutation of the coordinates associated to that code word either doesn't fix any single coordinate, or if it so happens that that code word is some multiple of the all ones vector, it actually is just the identity permutation, doesn't do anything. So we combine all of these things together. I've got a Butson code, which I obtained from my Butson matrix. And if it has this full propylinear structure, it is a Butson Hadamard full propylinear code. There we go. We finally got to the title. Now, this wouldn't be particularly complete without an example. So here we go. So take this Butson matrix over the fourth roots. It's 8 by 8. So this is in the, again, the exponent notation. So this is 0 is 1, 1 is I, 3 is minus, or 3 is minus I, and 2 is minus 1. So this is, if you translate that back into a phase 4 matrix, this is a Butson matrix. And if you were to take CH, as I described it before, remember that would be all of these code words plus all of the code words I get by adding an all ones vector as many times as I can to them. So there would be 32 of them altogether. Then this is going to be a set of vectors that we can call code words. And this is over Z4 or Z2 squared, but notice it's not additive. So therefore certainly not linear. because you can just take a look at the second vector here. If I add this to itself, that's not a code word in this set according to how it's defined. So this is not going to be a linear code, but can we give it some kind of propylinear structure? So it does have a structure that we like or are interested in. And in this case, we can. So here, this is just to go through the example. We're going to partition the code words. So the way this is partitioned, I've got 8 sets, C1 up to C8. And what I do is I just take the first code word and then everything I get by adding the all ones vector, that's one set. The second code word, everything I get by adding the all ones vector, and so on. So I've got these sets that all have 4 vectors in them. And then if I define my permutation map according to this table, where if I'm in that first set, it's the identity. The second set, it's this permutation of the 8 symbols. Then this does get me this full propylinear structure. So what I have is a code that has 32 code words in it. It's length 8. If you were to check, you would see it has a minimum Hamming distance of 4. It has a group structure isomorphic to this abelian group, Z8 times Z4. And then the actual permutation group just generated by the pi is the group Z8. So they don't have to be abelian, but this is just a relatively small example. Now, so I mentioned cocyclic matrices before, and then that kind of got lost in the wash, so time to bring them back. So if I have a cocyclic matrix, or really if I have a cocycle here, I guess, then you remember that the cocyclic matrix was just rows labeled by group elements and columns labeled by group elements. So you can see that this is a row labeled by a particular group element G, possibly multiplied by some scalar. I'm back into the kth roots here as opposed to the integer exponents. And then I can define my permutation of the coordinates in such a way that it sort of respects this, the way G acts on itself. And then I have this, the result of adding x to the vector you get by applying the isometry of x, the permutation isometry of x to y, and this second condition here as well. So this can be described, and the details of this are not so interesting. What's more interesting are the corollaries that arise from this. So the first of which is that if my cocyclic matrix happens to be a Butson matrix, then the corresponding Butson code or Butson Hadamard code is actually a full propylinear code. And we can describe the group operation according to this addition of vectors like so. And we can almost go the other direction, but not quite. If we start off with a Butson Hadamard full propylinear code, as long as we have this extra condition that the matrix is row and column balanced, then we can also say that the matrix is cocyclic. So by row and column balanced, what I mean is that every one of the kth roots of unity appears equally often in every row or column, with the exception of the first row and first column if you normalize the matrix.
So this example says 8 you have shown a second ago. Can you go back?
Yep.
It is not balanced.
The example of size 8, no, this one's not balanced and is not to my knowledge a cocyclic matrix, although I mean it possibly is equivalent to something like that. No. So C alpha is, so LH alpha is just the first row if alpha is 1. So it's just take the 0 vector and no, the purpose of defining the C alpha like this was purely so I could describe the permutation operation, this sigma x or this pi x, for each of the different vectors that are in the code. So just doing it according to this partition. That's how I could quickly write it down. That's all. Okay. So Now, I do want to talk a bit more about Butson matrices really than I do about codes for this particular audience. So I want to spend a little bit more time focusing on this next topic, where we take what's called a gray map and we generalize it a little bit. So this will be something that's familiar to coding theorists. Typically, the gray map, as it was originally defined, is some function that takes elements in Z4 to pairs of elements in Z2. And it's typically used to build binary codes out of Z4 codes. What we want to do is generalize this first to prime powers. So instead of just going from 4 to 2, we take p to the s. We take something, we reduce this down to just zp, but we have to scale up by a factor of p to the s minus 1. And then we generalize this further to deal with composite numbers. So take m that's not divisible by the same prime p, and then we'll have another map that maps elements in m p to the s, zm p to the s to longer vectors, but just in z m times p. So the benefit of doing this, if you're just interested in Butson matrices, you don't really care about the codes, is that assuming that my k is divisible by a product of primes, of course it is, if any of those primes have multiplicity more than 1 in here, what I can do with this map is just get rid of it, effectively. I can inflate my matrix by whatever appropriate factor I need to reduce my phase down to something that is square free. So if k is p1 to the whatever, up to pt to the whatever, I can reduce down to just phase L, where L is just the product of those primes, but nothing is square. And I just have to inflate by precisely the factor that I reduce my phase by. I inflate the order of the matrix. So this means I can start off with a Butson matrix that's n by n in the kth roots, and then I can inflate by a factor of k divided by L, but I build something that's in the Lth roots. So you've seen already, for example, people have mentioned the Turin map that goes from the 4th root matrices to the real ones. And this is a complete generalization of that. The Turin thing just falls straight out. But unfortunately, you can't completely drop a prime here. If you could, obviously that would be really interesting, but it would also mean that you would be constructing matrices that we know don't exist. So it's pretty clear that no general construction will be able to just completely drop these primes in every case. There are special examples where you can drop a prime like this. For example, Compton, Kragan, and Delaunay's map from the 6th root matrices to the reals, but that doesn't apply to every 6th root matrix as it was discussed. They have to be unreal. So some kind of complete mapping is never going to completely drop these primes, at least not in the generality that we're looking at here. So this is kind of as good as you can do. And then, of course, we apply this stuff to the BH codes and we track what happens too. But I want to talk a little bit about just this map and how we get to the bigger Butson matrices over the smaller phase. So start off with just looking at prime power, and then we'll kind of naturally generalize that a little bit. Okay, so we start off with elements in Zp to the s minus 1, order them. Okay, we've ordered them increasingly. And then again, we have this matrix D that we mentioned before. So we know that this is a Butson matrix. It's the, in this case, s minus 1-fold Kronecker product of the Fourier matrix with itself. And then we're going to be using this matrix as kind of a tool in our inflation. And the way we do it is we take some element in Z p to the s. We extend this to a vector that just has entries in Zp, but as long as it needs to be, p to the s minus 1. And we define the map like so, where we take whatever the number x is in Zp to the s, write it uniquely as some multiple of p to the s minus 1 plus a remainder b. That b tells me what row in LD that I use, and the a tells me what multiple of the all ones vector I add on. And this sort of generalizes the gray map from Z4 to Z2 squared to this Zp to the s minus 1 to Zp, or p to the s. So to see how this would work, to build a Butson matrix, what you do is you start off with a matrix that has your entries, in this case in the p to the s roots of unity. Then you take the exponent matrix, LH. You then add blocks of the same size by just adding the all ones matrix and add a block below it. Do that again until you get to p to the s minus 1 minus 1. So I've got now rows of length n, and I've got n times p to the s minus 1 rows. But for each entry, I'm now going to apply this map that you saw on the previous slide that will extend each of those entries to vectors of the appropriate length. And what you get is a square matrix that is of order n times p to the s minus 1, and the entries are all in the pth roots of unity.
Tu włączymy.
Tak, to złączyłem, okej.
Włączymy go, włączymy. Can you hear us? So please, talk here. There's a microphone here.
Oh, here.
Here. Yes, yes.
Oh, okay, right.
Yes. Okay, so
I'll crouch down a bit, so.
that should be fine.
Okay.
Should be fine.
Oh, I just need to get out of here.
Yes, the sound is back.
Okay, so anyway, I think I pretty much covered what I was talking about on this slide. Anyway, you build your larger matrix over the pth roots doing this. Now, can I full screen this? Sorry. How do I? Okay. Okay. So all that's really left anyway is to kind of generalize this to fully composite numbers rather than just prime powers. So here, when you take k in general, it'd be some multiple m of p to the s. And so m is now co-prime to p. Then again, we can write this uniquely as some multiple of p to the s plus some multiple of b modulo k, k being m and p to the s here. And again, if you do that, that allows you to define a map that now takes this number and sends it to a vector that is in m times entries are in z mp, which is p to the s minus 1 times as long. And you just have to apply this map from before to the part that is the part b, which is some number between 0 and p to the s minus 1. And then again, we have a times, okay, this p factor here times a vector of all ones. So it's sort of natural, but took a little bit of thinking about to get right. But this map, again, leads to exactly the same theorem if we just follow the exact same procedure from before by building the larger matrix LH, and then LH plus 1 and LH plus 2 and J and so on. And then you get from this Butson matrix, you apply this map and you get a larger matrix where I've gone from P to the S down to just P. So I've dropped every power of P that I can without eliminating it entirely. And because this map depends on P, if you want something completely general, just do it for every prime that divides K and do it repeatedly, and you get this map here. So this is like completely constructive. If you have any Butson matrix n by n over the kth roots, you just apply this map for every prime that you can, and you get something where you've inflated by a factor of K over L, but you've also divided the phase by that exact factor, which is nice. Now, what I would have gone on to say, but I might skip, I'll just do this last slide here, is the question, the natural question to ask if you're interested in codes is, does this preserve the property of being propylinear, full propylinear, if you apply this to your matrix to begin with? Unfortunately, the answer in general is no. Sometimes it does, but in general, this is not the case. But we do have at least one family where it does, where you do the usual thing where you go back to just P equals 2 and don't do anything too complicated. And in the case where you just apply the map that goes from 4m to 2m squared, then you actually do construct an isomorphism between the propylinear code that had a group structure in the Z4m case to the Z2m case where the code words are twice as long. So you can track the group structure applying this map. So I would probably, if I had a little bit more time, talk about what interests coding theorists, which is to do with distance and so on, but I think I'm just going to skip that and say thanks, but in Irish. So, Guramahagan.